Hello everyone and welcome back to another calculus video. In this video we are going to talk about properties of power series. We're going to start with theorem 6.2 and then we're going to look at some examples. Suppose that the two power series, the sum from n equals 0 to infinity of c sub n x to the n and the sum from n equals 0 to infinity of d sub n x to the n converge to the functions f and g respectively on a common interval I. Notice the common interval there. Then three things are going to result. The power series, n equals 0 to infinity of c sub n x to the n plus or minus d sub n x to the n converges to f plus or minus g on I. So if we're adding the two series together, it's going to converge to the sum of f plus g. For subtracting, then it's going to be the difference of f and g. And it's going to be on that common interval I. Part 2. For any integer m is greater than or equal to 0 and any real number b, the power series, the sum from n equals 0 to infinity of b times x to the m times c sub n x to the n converges to b x to the m times f of x on that common interval I. So here we're multiplying inside of that series. We've got b times x to the m multiplied by my original series here, c sub n x to the n. And notice that we're going to multiply that function f that series converges to, because remember that series c sub n x to the n converged to f. We're just going to multiply it by whatever that b times x to the m is. For any integer m is greater than or equal to 0 and any real number b, the series, the sum from n equals 0 to infinity of c sub n times the quantity b x to the m, and all of that's raised to the nth power, converges to f of b times x to the m for all x such that b x sub m is in I. So notice we're building a composite function here. I replace the x in the original series, c sub n x to the n, with b times x to the m to get this series, which means that it's going to converge to f of x, but x is going to be replaced by b times x to the m. So let's look at some examples. Let's look at example 1. We're combining some power series here. Suppose that the sum from n equals 0 to infinity of a sub n x to the n is a power series whose interval of convergence is negative 1 to 1. And suppose that a second series, the sum from n equals 0 to infinity of b sub n x to the n, is a power series whose interval of convergence is a negative 2 to 2. We want to find the interval convergence of the series, the sum from n equals 0 to infinity, of the sum of a sub n x to the n plus b sub n x to the n. So if we go back to our theorem, if I'm looking at the sum, it's got to converge on that common interval. So what do the intervals negative 1 to 1 and negative 2 to 2 have in common? So if I think about drawing these intervals on a number line, here's my negative 2 to 2, and then negative 1 to 1. So here's negative 2 to 2. Let me do negative 1 to 1 in a different color. So here's negative 1 to 1. If I look at the overlap, that overlap's going to happen between negative 1 and 1. So we would say that that sum has to converge in that common overlap, which would be from negative 1 to 1. So I'm going to say, therefore, the sum of those series converges on the interval from negative 1 to 1. And that's that common interval, what they have in common between negative 2 to 2 and negative 1 to 1. Part B is asking us to find the interval of convergence for the series from n equals 0 to infinity of a sub n 3 to the n x to the n. So now let's look at part B. We're looking at finding the interval of the series from n equals 0 to infinity of a sub n, 3 to the n, x to the n. I'm going to rewrite that as 3x to the n. So we could compare this to the geometric series, the sum from n equals 0 to infinity of a r to the n. And we know that converges if the absolute value of r is less than 1. So our r here is 3x. And this thing's going to converge if the absolute value of r is less than 1. So if the absolute value of 3x is less than 1, and we could rewrite that as 3x is wedged between -1 and +1. So we're going to get our interval of convergence to go from -1/3 to 1/3. So the interval of convergence is from -1/3 to 1/3. Just for fun, let's try another one. Let's say that we want to suppose that the sum from n equals 0 to infinity of a sub n x to the n has an interval of convergence of -1 to 1, and we want to find the interval of convergence of the sum from n equals 0 to infinity of a sub n x over 2 to the n. So if we know that the original goes from -1 to 1, and that's because this is, remember, power series can be written as geometric series. So let's compare to a geometric series. That r has to be less than 1. So in this case, my r is x over 2. The absolute value of x over 2 has to be less than 1, which means x over 2 is going to be wedged between -1 and 1. And if I solve for x by multiplying everything by 2, then that interval of convergence for that sum for n equals 0 to infinity of a sub n times x over 2 to the n would be from -2 to 2. Okay, notice in every case we're comparing to a geometric series, which means we cannot include endpoints. So let's look at example 2. We're going to use the power series representation for f of x equals 1 over 1 minus x combined with the combining power series to construct a power series for each of the following functions. In the first one, we're going to look at f of x equals 3x over 1 plus x quantity squared. So the first thing we want to do is see if we can rewrite this function as a geometric series. So let's do some tweaking here. So remember, with a geometric series, geometric series is the sum from n equals 0 to infinity of a r to the n, and it converges if r is less than 1, and that sum would be a over 1 minus r. So we're trying to rewrite 3x over 1 plus x squared in the form of a over 1 minus r. So let's see if we can do that. So f of x equals 3x over, how about 1 minus a negative x squared in the denominator? So we can see some r stuff coming out here. And we could think about that as 3x times 1 over 1 minus negative x squared. So then that tells me my a is 3x and my r is a negative x squared. So if I'm writing that as a geometric series, so the sum from n equals 0 to infinity, a is 3x, and r is negative x squared to the n. And I'm going to tweak this just a little bit. So I've got the sum from n equals 0 to infinity. This is 3 times x And this would be a negative 1 times x squared to the n. And then I can rewrite as negative 1 to the n times x squared to the n, which is x to the 2n. And notice I have an x here and an x here, so we can combine those. So we've got a 3. Oh, I forgot my sum sign. So it's the sum from n equals 0 to infinity of 3 times negative 1 to the n times x to the 2n plus 1. So let's find the interval of convergence. I'm going to use the ratio test. So to use the ratio test, I'm going to take the limit as n goes to infinity. It's the absolute value of a sub n plus 1 over a sub n. So I'm going to have the limit as n goes to infinity. I'm going to plug n plus 1 in for all the n's. And then divide by the original a sub n. And then we're going to simplify this. So I'm going to have the limit as n goes to infinity. So this is going to be 3 times negative 1 to the n plus 1 times x to the 2n plus 3 over 3 times negative 1 to the n times x to the 2n plus 1. And when I simplify, notice the 3's are going to cancel. I'm going to be left with a negative 1. And then when I subtract the exponents on the x's, I'm going to end up with 2n plus 3 minus the quantity 2n plus 1, which is going to be left with x squared. And when I take the absolute value of x squared, I'm going to be left with just x squared. And this is going to converge as long as the absolute value of x squared is less than 1, which means it's going to converge for values between negative 1 and 1. Okay, but remember, with the ratio test, you got to check the endpoints. So let's plug in x equals negative 1, and then we'll plug in x equals 1. So if I plug in negative 1, I'm looking at the sum from n equals 0 to infinity of 3 to the negative 1 to the n times negative 1 to the 2n plus 1. Let's simplify that. If I add the exponents together, I'm going to get negative 1 to the 3n plus 1. So if I plug in a 0, let's see what's going to happen. If I plug in a 0, I'm going to get negative 1 to the first. If I plug in a 1, I'm going to get negative 1 to the fourth. If I plug in a 2, I'm going to get negative 1 to the seventh. If I plug in 0, 1, 2, plug in a 3, I'm going to get negative 1 to the 10th. So I'm bouncing back and forth between odd and even exponents, which means my sum is going to diverge because I'm bouncing back and forth between negative 3 and positive 3. And if I add that up infinitely, it's going to always bounce and oscillate between those two. So it diverges at negative 1. And if we look at what happens at 1, we plug 1 in for x, have 3 times the negative 1 to the n. And I'm plugging the 1 in for this x here. So this is going to be 1 to the 2n plus 1. Well, 1 to any power is just going to be 1. So this is really just 3 times the negative 1 to the n. And again, that's going to be oscillating. It's going to be 3 times negative 1 to the 0 plus 3 times negative 1 to the first. So I'm still bouncing back and forth, which means the sum is diverging. So my interval of convergence is from -1 to 1, not including the endpoints. Now let's look at the second one. We're looking at f of x equals 1 over x minus 1 times x minus 3. Let's see if we can use partial fractions on this. So this is a over x minus 1 plus b over x minus 3. Or we can write it as the sum of two power series. So 1 equals a times x minus 3 plus b times x minus 1. So I have an equation that represents the variable in front of x, excuse me, the number in front of x coefficient, and then one that represents just the numbers. So I've got 0 on the left equals a plus b. I've got 1 on the left equals negative 3a minus b. I'm plugging this into an augmented matrix. First row is going to be 1, 1, 0. That represents a plus b is equal to 0. The second row is going to be negative 3a minus b equals 1. So it's negative 3 and negative 1, 1. Now I am going to do this off screen on my calculator. I'm going to type that in. I'm going to do RREF. And I ended up with 1, 0, negative 1/2, and 0, 1, and 1/2. So a equals negative 1/2, and b equals positive 1/2. So 1 over x minus 1 times x minus 3 equals negative 1/2 over x minus 1 plus 1/2 over x minus 3. So let's think about how we can tweak these to rewrite as power series. So I've got negative 1/2 over x minus 1 plus 1/2 over x minus 3. So remember our goal. I'll write it over on the right-hand side. The goal is to write a power series as a geometric, so AR to the n, and that's going to be a over 1 minus r. So we're trying to tweak this rational function to figure out what my a and my r is going to be. So what if I were to pull a negative out the bottom of each of these? If I pull a negative out, that's going to leave me with a 1 minus x. And then same thing in the bottom of the second one. If I pull a negative out, that's going to leave me with a 3 minus x. And I'm going to move that negative to the top. So this is going to be 1/2 over 1 minus x. So I can see what's coming out here. And this is going to be a negative 1/2 over 3 minus x. And in that second fraction, let's pull out a 3 here, and that leaves me with a 1 minus x over 3. So if I think about negative 1/2 divided by 3, if I do keep change flip, that's going to be negative 1/2 times 1/3, which is negative 1/6. So I can simplify that second fraction as negative 1/6 over 1 minus x over 3. So that first one we could write as a series from n equals 0 to infinity. My a is 1/2, and my r, remember this is 1 minus r, so my r is x. And then that second one, we could write as, I'm actually going to think about it as, instead of a plus here, let's think about it as a, or a plus negative, let's think about it as just a a minus. That way we're subtracting these series. So I'm going to think about 1/2 over 1 minus x minus 1/6 over 1 minus x over 3. So minus the sum from n equals 0 to infinity of a is 1/6, r is x over 3 to the n. So both of these are geometric series. This guy is going to converge, that first one, 1/2 times x to the n, as long as r is less than 1, well, my r is x. So as long as the absolute value of x is less than 1, which means it's going to converge on -1 to 1. That second one, that 1/6 times x over 3 raised to the n is going to converge. It's geometric if the absolute value of r is less than 1. And my r is x over 3, so that has to be less than 1, which means that x over 3 has to live between -1 and 1, or -3 is less than x is less than 3. And if I'm looking at the difference of those, we have to have that common interval. So if we think about that number line again, here's -3 to 3 for that second sequence, 1/6 x over 3 to the n, and the interval for that first one, which was 1/2 x to the n, was from -1 to 1. So what do they have in common? They have that area from -1 to 1. So therefore, this converges on -1 to 1, the difference of those two series. Now, if I want to think about combining those into 1, so we have the sum from n equals 0 to infinity of 1/2 x to the n minus the sum from n equals 0 to infinity of 1/6 times x over 3 to the n. Let's combine these into one summation. So n equals 0 to infinity. We could put them together into one that says 1/2 x to the n minus 1 over 6 x over 3 to the n, which is x to the n over 3 to the n. And we can see that these two terms have an x to the n in common, so let's pull it out. So we have the sum from n equals 0 to infinity of 1/2 minus 1 over 6 times 3 to the n. And all of that's multiplied by x to the n. In fact, if we wanted to, we could take that just a little bit further. So this is a 1/2 minus. And if we think about what 1/6 is, 1/6 is really 1 over 2 times 3. And then we have a 3 to the n times x to the n. And you can see how we have a 1/2 in common. So if I pull that 1/2 out also, so I'm going to pull the 1/2 out, and that's going to leave me with a 1 minus 1 over 3 times 3 to the n, which is 3 to the n plus 1 times x to the n. Let me fix my notation there. Or we could even pull the 1/2 out. So this is 1 minus 1 over 3 to the n plus 1 times x to the n. So there's lots of ways we could write and simplify these. Let's look at the next example. Let's say we want to consider the power series, the sum from n equals 0 to infinity of 2 to the n x to the n, and we want to find the function f represented by that series, and then find the interval of convergence for that series. So here's what I see. I could rewrite that sum from n equals 0 to infinity. So I have 2 to the n x to the n, which is the same thing as 2x raised to the nth power. And if I'm comparing to a geometric, so I'm going to rewrite my geometric up here, the sum from n equals 0 to infinity of ar to the n. That converges to a over 1 minus r if the absolute value of r is less than 1. So my a is 1, and my r is 2x. So I'm going to have 1 over 1 minus 2x. So this series is going to look like this as long as the absolute value of r is less than 1, but my r is 2x, so the absolute value of 2x has to be less than 1, which means 2x has to live between negative 1 and 1, or x has to be between negative 1/2 and 1/2. And that's the interval of convergence.